In this video, we're going to talk about Rolle's theorem. So we're going to say what Rolle's theorem actually says, and then we're going to justify why it is true. And so Rolle's theorem says the following. We're going to let f be a function that satisfies the following three conditions. So first, f is continuous on the interval a to b, and that needs to be a closed interval. Second, f is differentiable on the open interval a to b. And third, f of a equals f of b, which says that we are starting and ending at the same y-coordinate. And then if these three are satisfied, then there exists a number c in the open interval from a to b such that f prime of c equals 0. So in other words, there's some point where the derivative is 0. So now if you look at graphs, Rolle's theorem is a little bit easier to understand. And so the idea of Rolle's theorem is if we have these 2 points, a comma f of a, and b comma f of b, where we know the y-coordinates are the same. And then all Rolle's theorem says is if, however I draw the graph between these 2 points, if I am continuous and differentiable, I have to have a point where the derivative is 0. And so I have this point where the derivative then is 0. So this would be where c is at. The way I think of this is what comes up must go down. And so we know that we start at a certain y value and end at a certain y value. And so if we went up, we had to turn around at some point to come back down. And since we are differentiable, that place where we turned around will be a point where the derivative is 0. Now, we do need all of these conditions. If you are not continuous, then the graph could do something like the following. It could have a place where you just have a hole. And so that's why continuous is needed, is that we can't have any jumps. And then differentiable is needed because you could have a corner show up. And so this would be where our point C would occur, but it's not got a derivative defined there because we have a corner there. And so basically the first 2 conditions are just saying that we've got some nice smooth graph between A and B, and the third condition is saying the y-coordinates line up. So then we have to have a place where the derivative is 0. So that's the idea behind Rolle's theorem. It's fairly intuitive once you think about it, and just that we were lying on the same horizontal line. And so if we started there and ended there, we had to have turned around some point. And that turnaround point is our value c. Now, Rolle's theorem is used to prove that there is exactly one solution to equations. So that's one place it's used, and that's what we're going to focus on in this video. And so we want to prove the equation x cubed plus x minus 1 equals 0 has exactly one real solution. So we want to prove that this occurs for exactly one real number. Now the way we do this is actually in 2 parts. The second part is where Rolle's theorem is going to come up. The first part is going to use the intermediate value theorem. If you don't recall what the intermediate value theorem says, I'm going to restate it for you right now. So the intermediate value theorem, which I abbreviate as IVT, says the following. If f is continuous on the interval a to b, then for any value between value n between f of a and f of b, there exists a point C in the closed interval a to b where f of c is equal to n. Now, this is stated a little bit different than I stated it before, but this is the theorem that basically says you have to hit every point between f of a and f of b. So we've got to hit everything in the middle is the idea, because we can't lift our pencil, and so we're hitting every value. That's what the intermediate value theorem says. And I'm stating it in a bit different words here, but we're going to use the intermediate value theorem to prove there is at least one solution. We have done this before, so if you go back to the intermediate value theorem lecture, we did talk about doing this before. We're going to do it again now. So we want to first show there's at least one solution. So to show there's at least one solution, we're going to let f of x be equal to x cubed plus x minus 1. So we're just setting it equal to our polynomial. So our solutions are when f of x equals 0. And so notice f of x is continuous for all real numbers. Okay, it's a polynomial, so it's continuous everywhere. And so because of that, we're going to be continuous on any open interval, closed interval, a to b. Okay, so now what we do is we're going to find a place where we're less than 0 and a place where we're greater than 0. And then that forces us to be 0 somewhere. And so notice f of 0, if I plug 0 in, I get 0 cubed plus 0 minus 1. So I get negative 1, which is less than 0. If I plug in 1, I get 1 cubed plus 1 minus 1, which is 1. And that's greater than 0. So I'm less than 0 at the x value of 0 and greater than 0 at the x value of 1. And so then by the intermediate value theorem, which again I'll actually write out its name now. So it's the intermediate value theorem. There exists a point C in the interval 0 to 1 where f of c equals 0. Okay, so all of this is review from what we've done before. So we've proven that we've got a point where we get 0. There's at least one. Now, Rolle's theorem is used in showing there's at most one. Now, the idea here is we're going to do what's called a proof by contradiction. If you've never seen a proof by contradiction before, this will look a little odd. But the idea behind it is we're going to assume that we're wrong, so assume there are two solutions, and show that something goes bad if there are two solutions, which then tells us that our assumption just was wrong. So we're going to look for two statements that contradict each other, that can't both be true at the same time, and then that will tell us that our assumption is wrong. And so, like I said, we're going to assume there are two solutions, C and D. Then f of c is 0 and f of d is 0. Okay, so we've got these 2 points that have the same y-coordinate, c and d. And so on the interval c to d, the closed interval c to d, f of x is continuous. It's continuous everywhere, so it's certainly continuous there. Also, f of x is differentiable on the open interval c to d. Once again, polynomials are differentiable everywhere, so the fact I'm saying from c to d it's differentiable is not saying anything. I'm just using the fact that it's always differentiable. Okay, and so we have these two pieces, but we also know that f of c equals f of d. They are both 0, so they're equal. And so these are the three conditions for Rolle's theorem. We have to be continuous on a closed interval, differentiable on an open interval, and have the same y-coordinate at the start and the end, which we meet all those conditions. So by Rolle's theorem, there exists a value, and I'm going to call it k because I'm using c for something else. So there exists a value k where f prime of k equals 0. Okay, so all we've got then is we found that the derivative is 0 somewhere at this value k. But what we're going to do now is show that doesn't actually happen. So observe that f prime of x, well, let's remember what f of x is. F of x is x cubed plus x minus 1. So if I take its derivative, I get 3x squared plus 1. And that's always greater than or equal to 1, because 3x squared is always non-negative. I'm adding 1 to it. So this is always greater than or equal to 1. So f prime of x does not equal 0 for any value of x. Well, that's a problem because we just said there was a value k where the derivative is 0, and we also just said it's never 0. So those can't both be true. That is where our contradiction is coming in from. And so it's coming from this fact that we can't both have a derivative of 0 and always have a positive derivative. And so that means what we assumed to begin with must have been wrong, which our assumption was this part right here, that we assumed that we had two solutions. So that can't be true. So there cannot be two solutions. Well, if there cannot be two solutions, and there is a solution, then there must be one. So therefore, there is exactly one solution. Because we know there is one from the intermediate value theorem, and we know there is not two, so there's only one. And that's the idea behind Rolle's theorem, is just this argument that we just did. Now we're going to do a second one of these problems, just for additional practice. The flow of the argument goes largely the same, so I am going to go through it slightly faster. But we're going to do much the same thing. So we want to show the equation e to the x plus 2 equals 2x squared has a unique solution in the interval negative 2 to 0. So we want to show there is a unique solution to this expression. And a unique solution means exactly one. So this is just another way of phrasing what we asked before. So the first thing we're going to do is we're going to rewrite this as e to the x minus 2x squared plus 2 equals 0. So just moving the 2x squared over. So now we're really just saying when is this expression e to the x minus 2x squared plus 2 0, and that's what we're going to work with. So first we're going to show there's at least one. So once again, this is going to be the intermediate value theorem. So we're going to let f of x be e to the x minus 2x squared plus 2. And so we want to show that this is 0 somewhere. Okay, and so first notice that f of x is continuous on the interval negative 2 to 0. So e to the x is always continuous, and negative x squared plus negative 2x squared plus 2 is always continuous. And the sum of continuous functions is continuous, so this thing's always continuous. So it's continuous on that interval. So it's continuous on negative 2 to 0. If we plug in points, if we plug in 0, we get e to the 0 plus, minus 2 times 0 squared plus 2, which is going to be 1 plus 2. So we get 3, which is greater than 0. If you plug in negative 2, you get e to the negative 2 minus 2 times 2 squared plus 2, which is e to the negative 2 minus 2 times 4 plus 2. And this then becomes e to the negative 2 minus 8 plus 2, so minus 6. So 1 over e squared minus 6. Now, you might not know exactly what value that is, but 1 over e squared is 1 divided by a number greater than 1. So this expression is less than 1, and I'm subtracting 6 from it. So that's going to be less than 0. If you're curious, this is about negative 5.86. So it's less than 0. Okay, so we see that we are greater than 0 at 0, and less than 0 at negative 2. So by the intermediate value theorem, there exists a value c where f of c equals 0. Okay, so the intermediate value theorem tells us that we've got to be 0 somewhere. So now we're going to show the at most step. And so that's where we're going to use Rolle's theorem. So, as before, we're going to suppose we have two solutions. So suppose C and D are two solutions in the interval negative 2 to 0. So that is C and D. So that is negative 2 is less than C and D, and that's less than 0. And f of C equals f of D equals 0. Okay, so we're assuming we have two solutions. And then notice that f of x is continuous on the closed interval C to D. The reason for that is it's always continuous, so it's certainly continuous on C to D. And f of x is differentiable on the open interval from C to D. So remember f of x is e to the x minus 2x squared plus 2. The derivative of that expression always exists, so it's differentiable everywhere as well, so it's differentiable on C to D. So we meet our three conditions. We're continuous on the closed interval C to D, differentiable on the open interval C to D, and f of c equals f of d. They're both 0. And so then by Rolle's theorem, there exists a value k where f prime of k equals 0. Okay, so all of that, basically the same idea we did before. Now this value k is between c and d. But it's also then between negative 2 and 0, because c and d are between negative 2 and 0. And so just note k is in the interval negative 2 to 0, because it's between c and d. And so observe that f prime of x equals, remember the function is e to the x minus 2x squared plus 2, so its derivative is e to the x minus 4x. Now observe the following. On the interval negative 2 to 0, negative 4x is going to be greater than 0. Now the reason for this is that if I plug in a value in negative 2 to 0, it's negative. So I have a negative number times negative 4, so it's a negative times a negative, which is positive. So on that whole interval, negative 4x is going to be greater than or equal to 0. Then, e to the x minus 4x is going to be strictly greater than 0, because e to the x is always positive, and I'm adding a non-negative thing to it. So e to the x minus 4x is greater than 0 on the interval negative 2 to 0. So that is f prime of x is strictly greater than 0 on the interval negative 2 to 0. Well, that contradicts Rolle's theorem, because Rolle's theorem said that we found a value k where the derivative is 0. And so these can't both be true. And so because they can't both be true, our assumption at the beginning was wrong. And so, in other words, so therefore, there is at most one solution because we can't have two. So we can't have two solutions, so there's at most one. Hence, because there is at most one solution and there's at least one solution, there is exactly one solution. So we found that there is exactly one solution.